For this lab, you'll need a few different items. You'll need a 50 milliliter round bottom flask. You'll also need a stir bar as well as a heating mantle and hot plate, which are not shown here. You'll also need a condenser with the appropriate tubing, cyclohexene, 30% hydrogen peroxide, aliquot 336, which you can read more about in the lab procedure, potassium bisulfate, which has the formula KHSO4, and finally, you'll also need sodium tungstate, which has the formula Na2WO4. In the next step, we're going to weigh out about 0.5 grams of sodium tungstate. So I'm just going to zero this weigh boat, and then I will add about 0.5 grams of sodium tungstate to it. And you can find the exact mass that I measured out in the lab data document. Now we're going to add the sodium tungstate that we measured into the 50 milliliter round bottom flask, and you'll notice I already added the stir bar to the flask. Next, we're going to measure 0.5 grams of aliquot 336, which is our phase transfer catalyst. Now, this is a viscous liquid, so we are going to add it directly to the 50 milliliter round bottom flask. So here you can see that I'm going to zero the round bottom flask in the balance. And then I'm going to add the aliquot 336 until I'm as close as possible to 0.5 grams. Now, we are going to use a glass pipette to transfer the aliquot 336 to the round bottom flask, but it's still a little difficult because the aliquot 336 basically has the consistency of honey. It's very sticky. It is not easy to draw up into the pipette. It also is released pretty slowly into the round bottom flask. So this process does take some time. Next, we're going to weigh 11.98 grams of 30% hydrogen peroxide. And this time we can use a separate beaker in order to weigh out the amount we need. And then we'll transfer it to the round bottom flask in the next step. Now, you do want to be careful with 30% hydrogen peroxide because it can burn your skin. The kind we use at home to clear out cuts and scrapes is 3% hydrogen peroxide. So this is 10 times as strong, so it's very corrosive. So here I'm just adding little bits at a time until I reach 11.98 grams. You can find the exact mass that I measured here in that same lab data document on the Canvas assignment page. Now I'm going to add the 30% hydrogen peroxide to the 50 milliliter round bottom flask. And I'm going to show you what the solution looks like right now. So the phase transfer catalyst, the aliquot 336, is in there, as well as sodium tungstate and hydrogen peroxide. Now we're going to weigh about 0.37 grams of potassium bisulfate. So this is a powder, so we can use a weigh boat again for this step. And first, I'm going to zero the weigh boat and then add about 0.37 grams of potassium bisulfate. You can find the exact amount that I weighed out again in the lab data document on the Canvas lab assignment page. Here I just wanted to show you that the potassium bisulfate is quite chunky or clumpy. So it is a little bit difficult to weigh exactly 0.37 grams, but we're going to try our best here. Now we're going to add potassium bisulfate to the same round bottom flask. So I'm just going to bend my weigh boat and pour the solid in. Finally, we're going to weigh out 2 grams of cyclohexene. Now for this step, I'm using a clean separate beaker to weigh 2 grams of cyclohexene. So I already zeroed the beaker, and here's the cyclohexene we're going to use. Now, if we were in person, we would have saved our cyclohexene that we synthesized in Chem 261. So remember, the last lab we did in Chem 261 involved synthesizing cyclohexene from cyclohexane and sulfuric acid. But since we're online, I'm just using cyclohexene that was already available in the lab. Now we're going to perform a reflux. So I have my round bottom flask sitting in a heating mantle on top of a hot plate. Now we're going to only use the stir function on the hot plate. We're not going to turn the heat on. Instead, we're going to heat the mixture using the heating mantle on top of the hot plate. So before we turn the heat on, I wanted to show you what the mixture looks like. It's sort of a pale yellow, and you can see the stir bar is starting to mix everything together. So now I've added my condenser on top of the round bottom flask. So I'm going to turn the heating mantle on, and I'm turning it up about halfway. And you'll notice that the condenser is also connected to the water tap in the back of the hood, so the green tap. And water is going to flow from the bottom of the condenser out through the top of the condenser to keep everything cool. So here is what the solution looks like as it's heating. So everything is mixing together really nicely. So one thing to keep an eye on during the reflux step is what's called the reflux ring, which is the top of the condensation that's occurring in the condenser. So as we reflux, that ring can rise up to the top of the condenser. We want to make sure that does not happen. We're going to reflux for a total of 1 hour, but about halfway through, at the 30-minute mark, I'm going to rinse down the insides of the condenser. So if anything is rising up the column of the condenser, I can wash it back down into the round bottom flask. So I have my beaker of water with a disposable pipette, and I'm just going to, again, rinse the inside of the condenser. So I'm moving the pipette around the top of the condenser, and I'm only using a little bit of water, not too much. Once an hour has passed, this is what the solution looks like. So it is pale yellow in color, everything is mixed nicely. So now I can turn off the heat on the heating mantle and remove everything from the hot plate. So I'm turning off the heating mantle, and then I'm going to very carefully move the reflux apparatus off to the side. So up above you might not be able to see, but there is a clamp holding the condenser. So I just moved that up and tightened it, and now I'm going to lower everything into this cork, and I'm going to let that cool for a little bit. I'm also going to remove the heating mantle from the hot plate because I want to start heating up some water for a future step. So I've got my beaker of water there. And the heating mantle actually isn't too hot, but I'm still exercising caution as I remove it so I don't burn myself. And I'm placing my water on the hot plate, and I'm going to turn up the heat on the hot plate. Once everything is cool enough, I'm going to remove the water layer in my round bottom flask, and I'm going to transfer it into a clean beaker. I'm going to try my best not to transfer any of the aliquot 336, our phase transfer catalyst. That's going to remain in the bottom of the round bottom flask. So everything that I'm transferring here should be clearish white, maybe a little foggy. We shouldn't see any pale yellow in our beaker. So I wanted to show you the difference in the water layer versus the phase transfer catalyst at the bottom. So you can kind of see that there is a yellow sort of gunk in the bottom there, and that is the aliquot 336 that we're trying to avoid transferring into the beaker. After removing the final bit of water from the round bottom flask, you can see that the aliquot 336 is left over in the bottom. So the stir bar's in the middle there, and the aliquot 336 is a yellow color. I'm now going to remove the water that I was heating from the hot plate. Notice that I'm using beaker tongs in order to prevent burning myself. I'm also going to measure out a few milliliters of this hot water. So I've measured out about 5 milliliters of this hot water, and what I'm going to do is use this hot water to dissolve any remaining product in the round bottom flask. So I'm just pouring it into the flask. I apologize, it's a little blurry. And then I'm just gently swirling the hot water and moving it around the round bottom flask. So now we're capturing any last bits of product in there. Next, I'm going to transfer any of the water layer into that same beaker off to the right. And again, we're going to leave the aliquot 336 behind. Now I'm going to place the beaker into an ice bath. So I've prepared a small ice bath, and I'm going to gently place the beaker in there, and this will allow crystals to form. So I'm going to leave this for a little while and let the crystals develop. While I wait for my crystals to form, I'm going to set up my vacuum filtration system. So as you'll recall, a vacuum filtration system involves a Buchner funnel in an Erlenmeyer flask, and then that Erlenmeyer flask is connected through rubber tubing to another Erlenmeyer flask that's going to be our vacuum. And then that middle Erlenmeyer flask is also connected to a vacuum line, which is in yellow. So we can turn on the vacuum line, and that will suck air through the system, and that allows us to separate any liquid from our crystals. So I have a piece of filter paper in the Buchner funnel on top, and what I'm going to do is add just a little bit of water to that filter paper to get it started, and then we're going to add our crystals. Now we're ready to add our crystals to the Buchner funnel. So here you can see that we've developed quite a few crystals in the beaker. There is still some liquid in there though, which is why we're using the vacuum filtration system. We can separate the liquid from the product, and the liquid is going to fall through the filter paper to the Erlenmeyer flask below, leaving the crystals behind in the funnel. So to help remove the crystals from the beaker, I'm just going to use a small spatula. So here are the crystals. You'll notice they're in a clump. So what we want to try to do is break that up to increase the surface area so that more liquid will fall through into the Erlenmeyer flask below. If we leave it in a clump like that, then water will be trapped within the crystals. So again, we want to try to break it up as gently as possible and spread the crystals out to remove as much liquid as possible. While I wait for the crystals to dry, I added another beaker of water to my hot plate so I can use it for recrystallization in the next step. Before I perform recrystallization of my crystals, I want to see how much of the crude product I obtained. So this is the product that is not completely pure yet. So I'm just going to weigh a beaker and then add my crystals to that beaker and get the total mass. Now that I have the mass of my empty beaker, I'm going to add the crude product to that beaker. So again, the crude product may have impurities in it, and that's why we're going to recrystallize it in the next step to try to remove any impurities. And in fact, when I was looking at the crystals, I noticed a little bit of yellow left over in some spots, which could be part of the aliquot 336, which would contribute to any impurities. But here I'm just gently removing those crystals from the filter paper. And again, you want to gently remove these crystals. You don't want any filter paper pieces to end up in your product. So here's a closer look at our crystals. They're mostly white, but again, I did notice some pale yellow crystals in there, which could be impurities. So we're going to recrystallize it. But first, let's weigh our crude product and see how many crystals we have in this first step. Now again, this could include some impurities. You can find this data in the lab data document on the Canvas Lab assignment page. I did save a little bit of my crude product so that I could get a melting point later on, and that will also help me determine how pure my sample is. Now it's finally time to recrystallize our crude product. So again, I've been heating some water on the hot plate. I'm going to add some of that water to my beaker of crystals. Not a lot, just enough to dissolve the crystals again. And then I'm just going to stir the crystals so that they dissolve. So the great thing about the recrystallization step here is any aliquot 336 that was present in our crude product should be left behind. And you can actually see that aliquot 336 is settling on the bottom of the beaker. It's not dissolving with the crystals. So this is a great method for purifying your crystals. So now I'm going to pour my solution into an Erlenmeyer flask for recrystallization. And again, the aliquot 336, the impurity, is going to be left behind in the beaker. So here you can see that aliquot 336, which is sort of waxy, it's left behind in our beaker. So we have removed the impurity from our crystals. Now we're ready to add the Erlenmeyer flask to the ice bath for recrystallization. Now I waited until the water was about room temperature because that promotes slow cooling, which will help crystals to form. So we're just going to leave this in the ice bath and then we'll go on to the next step. So now that our crystals are formed, we can use our vacuum filtration system to separate any leftover liquid from those crystals. Now I did clean out my Buchner funnel to remove any of the crude product that might have been left over from our previous vacuum filtration. I also added a new piece of filter paper so we don't have any cross-contamination. So I used a spatula again to help me remove the crystals from the bottom of the Erlenmeyer flask, and then I'm going to try to pour them into the Buchner funnel. And I usually aim for the center of the filter paper so that the crystals don't go over the sides of the filter paper. And I'm just going to try to guide the crystals out, which can be a little tricky in an Erlenmeyer flask due to the curved edges. To remove any last crystals that might still be left in the Erlenmeyer flask, I just added some cold water and poured it back in. Let's take a look at our crystals. So this looks much better. I don't see any pale yellow in the crystals. I'm also going to spread them out to encourage faster drying. And I'm also just checking if there are any pale yellow crystals, but I don't see any, so that is good. That means our product is most likely pure, although we can always check using the melting point. Similar to before, I'm going to grab a clean beaker and pre-weigh it, and then I'll add my recrystallized product into this beaker and weigh everything together. Now I'm going to add my recrystallized product into that small beaker I just weighed. And again, this looks much better. We don't have any pale yellow in the crystals. So again, we can test the purity using a melting point, but first I'm just going to lightly scrape out the crystals into the beaker, being careful not to remove any of the filter paper. Now I'm going to weigh the beaker with the crystals, and later I can subtract the mass of the empty beaker to find the mass of my recrystallized product. Now I'm going to measure the melting point of my crude product as well as the recrystallized product. So I've grabbed a melting point tube, which is open on one end and closed on the other. I'm using the open end and tapping it into the crude product to get some into the tube. So I'm trying to focus it here. It's hard to focus on. And then what I'm going to do is turn over the capillary and tap the closed end onto the countertop. And that's going to allow the product to sink to the bottom of the capillary. And then we'll place that into our melting point apparatus and we will see when the product melts. I'm also going to do the same thing with our recrystallized product. I'm just tapping a little into the open end of the melting point capillary, turning it over, and then tapping it so that the product goes into the bottom of the tube. So now I'm going to set up our DigiMelt and track the melting points of our crude product and our recrystallized product. So I'm going to start at 130 degrees Celsius. I'm expecting the melting point of a pure product to be 152 degrees Celsius. So I'm giving myself a little wiggle room. I'm also going to set the ramp rate to 2 degrees Celsius per minute. And then I'll just set the final temperature at 250 degrees Celsius. It doesn't really matter as long as it's higher than our expected melting point. Now I'm going to place the capillaries on the top and you can see them through the viewfinder. So I jumped ahead a little bit. I skipped the preheating part here. So now we're at 130 degrees Celsius. I'm putting the crude product on the left and then the recrystallized product on the right. So what we'll do is focus in on those two capillaries, and you can also see the temperature off to the right. So now we're going to start ramping up the temperature, and what I would like you to do is try to determine where the crude product and the recrystallized product start melting, and that might be at different times, and then track when they stop melting, so when they're completely liquid. You might notice that the crude product has a lower melting point, and it might have a broader melting point range because it might have impurities in it. So something to keep in mind as you track the temperature.